Welcome to day one of our distance learning. Today we're going to learn about electrical power. Electrical power is one of the more important terms in this unit because it will link this unit to all the other units that we studied this year. Before we talk about electric power, it's important to remember the two terms we just learned, voltage and current. When you talk voltage for a battery, remember that it's telling you the amount of energy that you can get per unit of charge from your battery. So if you have a 9-volt battery, that means that each coulomb that comes out of your battery will deliver 9 joules to the external environment. As current is flowing from your battery, remember that current measures how much charge is flowing per second. So oftentimes current will be measured in amps, and amps is just a measure of coulombs per second. So 2 amps means 2 coulombs each second. Okay, things really get important when we combine these two things together. So we have current and we have voltage, and we're going to multiply the two terms together, and hopefully you see what's going to happen. Charge is going to cancel on the top and the bottom when we multiply these, and we'll be left with energy over time. Energy over time hopefully is familiar to you because that is the term we've used twice before, and that is power. So if we multiply current and voltage, we get power, our electrical power. And based on conservation of energy, that electrical power can turn into all different types of energy. So this work that we've had before could have been kinetic energy or potential energy or heat, or later, light and sound. It could all be created through electricity using this new formula that is a byproduct of the definition of current and voltage. So when you multiply current and voltage, you get power, you get energy per second. Here are some of the important transformations. We have toaster, fan, lamp, radio, and Tesla climbing a hill. Take a moment and try to think about what type of energy is being created by electricity for each of these devices. Okay, so for your toaster, obviously it's creating heat. For a fan, it's creating kinetic energy. For a lamp, it's creating light. For a radio, sound. And a Tesla climbing a hill is turning electrical energy in the potential energy gravity. I'd like you to do some math with this. So I'd like you to find out how much current is used by that hair dryer and also how much energy is used in 15 minutes. So we do our two formulas. We do power equals VI. The power, it tells you, is 1875. The voltage for an American outlet is 120, and we solve for I. To get the energy, we do power equals work over time. Again, work is the energy. We put our power in, and we put our time in seconds. So 15 minutes would translate into 900 seconds. You'd multiply together and get the amount of work done by your hair dryer, and that should come out in joules. You should get a very large answer for this. When I did it, I got about 1.7 million joules of energy. Hopefully you remember that earlier this year, we found out how much electrical energy costs us from our power company, and at this time in history, in this area of New Jersey, it's about 14.94 cents for 1 kilowatt hour of energy. Remember, 1 kilowatt hour is equivalent to 3.6 million joules. So with our hair dryer and with many of our electrical devices, we'd like to figure out how much money it's going to cost us to run this device. So we got an answer of about 1.7 million joules of energy. We convert that into kilowatt hours. And then we multiply that by 14.94 cents. And that will tell us how much money it's going to cost to run that hairdryer for 15 minutes. And when I did this, I got around 7 cents. So for about 7 cents a day, you can run your hairdryer for 15 minutes. Not bad. Okay, I'd like you to try something similar with a light bulb. Okay, so we're going to use our power equals voltage times current. Our voltage is 120. Again, that's the standard for American outlets. It tells you on the bulb that this is a 100-watt light bulb, and you could find the amount of current used by the light bulb. We'd also like to find the amount of energy that we use if we leave this light bulb burning all the time. So let's say we have our 100-watt light bulb. Let's say we're going to let it run for a full year. Make sure you turn your number of days into seconds. And for 1 year, it's about 31,536,000 seconds. You solve it for W and get the energy used for 1 year. Convert that answer from joules to kilowatt hours, and from kilowatt hours into cents, and then probably you want to turn that into dollars. When I did this, I got about $131 to let that light bulb burn all year long. So if you get yelled at for leaving lights on, it's probably valid. You're costing your household $131 a year to leave that light burning. Okay, the best thing you could do is to turn the lights off, but the other thing you could do is change your type of light bulbs. So this is the older incandescent style that we were just looking at. This is called the fluorescent bulb, and this is called an LED. If you look, this is a graph of the energy uses for 3 different types of bulbs. This happened to be a 60-watt incandescent bulb, and you can see for the compact fluorescent, it was less than 20 watts. And for the LED, it was less than 10 watts. So the same brightness, we get a lot more efficiency with the LED. And the reason is these old incandescent bulbs, instead of creating just light, would also create lots and lots of heat. Okay, here's another problem that you could try. This time we're going to be heating up some water, and I'd like to see how much it's going to take in terms of time and also in terms of cost. I'm going to post this problem on the slideshow, and I'd like you guys to work through the details and take a picture of your work and share it with me via that slideshow. Finally, I just wanted to show you guys, if you're spending time over this extended isolation, where you're watching things like Netflix on your different devices are more efficient at streaming video. And you'll notice the most efficient is an Apple TV, which is able to display HD video, 1080p, with only 2 watts of electricity. You'll notice if you're streaming it on a PS4, it's about 89 watts to do the same job. So again, if you wanted to figure out how much it would cost you to stream movies, you'd use your power equals work over time, your power, and then if you were doing for like a whole hour, you put in 3,600, get your answer, multiply by how many hours per day you're actually streaming the video for, and then convert the joules into kilowatt hours and then into cents. And you'll notice that the PS4 is going to be a lot more expensive to run than your Apple TV. One of the other things I'm going to put on your slideshow is I'm going to ask you guys to find an appliance around the house On the appliance, see if you can find the information. If it doesn't tell you voltage, you can assume it's 120, and then look for the wattage. And what I'd like you to do is figure out how much it's going to cost to run whatever appliance you find for however long it's run in your house during the course of a typical year. So make sure you send me a picture of the appliance showing the wattage, and make sure you show me a picture of your work. Anyway, that's all we're going to be doing for day one. I wish you guys the best, and I hope to see you all soon.